Welcome. Hello, everyone. Welcome to this second lecture of the third edition of Current Topics in Heritage Science, organized by emerging professionals within the E-RIHS Academy. Today's lecture is Laser Cleaning Heritage Objects and Monuments, Tailored Solutions for Demanding Restoration Challenges. Our speaker is Dr. Paraskevi Pouli. She is a senior researcher in the Photonics for Heritage Science group at IESL-FORTH. She specialized in the developing innovative laser technologies aimed at the restoration of art and antiquities. With a background in laser physics, her research focuses on developing cleaning methodologies to tackle various restoration challenges. A key aspect of her work involves assessing treated surfaces and monitoring ablation processes. She has relied on behalf of the FORTH, the laser cleaning project at the Acropolis in Athens, working in collaboration with the Acropolis Restoration Service and the Acropolis Museum. Together, they developed an innovative methodology and a specially designed laser system to safely remove pollution crust from the dedicated marble sculptures. This collaboration earned the Acropolis Museum and FORTH the 2012 Keck Award from the International Institute for Conservation of Historic and Artistic Works for their work titled Laser Rejuvenation of Caryatids Opens to the Public at the Acropolis Museum, a link between ancient and modern Greece. In addition to her research efforts, she organized the OPTO-CH training activities initiated by FORTH, and is also responsible for the laser cleaning activities within the framework of transnational access offered by FORTH as part of the E-RIHS Greece and E-RIHS.eu initiatives. Thank you so much for accepting our invitation, and the floor is yours.
Thank you very much, Diego. Good afternoon to everyone. As already Diego mentioned, I am Paraskevi Pouli, or Vivi for my friends, and I'm a researcher at the Institute of Electronic Structure and Lasers of FORTH. And I have to say that I'm indeed very happy and very honored to be able to present today to this workshop some tailored solutions for demanding laser cleaning restoration challenges. I have been informed that the audience today spans across the globe, so allow me to use a couple of minutes to present very briefly FORTH, the Foundation of Research and Technology Hellas. We are situated in the southern eastern corner of Europe, in Heraklion, which is the capital city of the island of Crete. Heraklion is a multicultural city with plenty of Aeneasian monuments, as you can see the coastal fortress here in the photo. While nearby, we have the the Minoan Palace of Knossos, as a testimony of one of the most ancient civilizations in Europe, the Minoan civilization, which was developed in the Bronze Age between 3100 and 1100 before the Common Era. FORTH is a foundation for research, ranks first among the other research institutes in Greece and amongst the most known in Europe. The Institute of Electronic Structure and Laser, the institute that this team I belong, and the work I will show you today, is one of the founding institutes of FORTH since its creation 40 years ago. So, in this institute, in 1994, we had the first experimental attempt to remove aged varnish layers and dark soot deposits from a Byzantine wooden icon using a nanosecond ultraviolet excimer laser beam at 248 nanometers. Here you can see the result. And I have to say that since then, FORTH has been in a wonderful journey that lasts for almost 30 years and offer us a lot of excitement, experiences, and knowledge. Before discussing the plenty advantages of laser cleaning, I would like to briefly remind some Advantages and disadvantages of the conventional cleaning techniques, the techniques that conservators can use to remove unwanted layers and materials. First of all, we have mechanical cleaning, mainly scalpels. They are a very affordable solution, which don't necessitate a high level of experience, exceptional dexterity, and of course, lots of time. It is highly dependent on the user's contact with the object. It provides immediate control and feedback, maintains a high standard for environmental and health safety, but it does not have any self-limiting features. Then we have microabrasive or steam cleaning. This is also an affordable solution. It can be employed in large scale projects, but shows very low environmental and health standards. And of course, it is again non-self-limiting. Last but not least, we have chemicals, which are broadly used for plenty of applications, as for example, for the removal of aged varnish layers on paintings. And their major drawback is the lack of control, as there is always the danger of penetration of the chemical into the bulk of the object of the surface and affecting the deeper layers. It has low control and demanding standards for environmental and health safety. And then we have lasers. Lasers is the acronym for the light amplification by stimulated emission of radiation. This is a unique type of light and was reconstructed in the laboratories in the early 60s, while the earliest testimony of its use for cleaning of heritage applications goes back to early 70s and is recorded by John Asmus and an Italian team guided by Lazzarini in Venice. The important is to see what is laser and how lasers can be compared to a common light bulb. First of all, this is a monochromatic light. Each laser beam has its own characteristic wavelength, its own unique color. As a result, it does not interact with all the materials in the same way, and thus it offers exceptional selectivity. It can be focused through an appropriate lens, for example, to a point, and thus all its energy can be concentrated and induce all these phenomena that will eventually ablate the radiated material. It can be highly directional, again using appropriate optics, as for example prisms or mirrors. It can be directed and handled, allowing for extra versatility, i.e. it can reach distant surfaces or go around objects of high relief. The beams can be combined, laser beams can be combined and allow us to exploit new possibilities. And they can be easily guided, as for example through an optical fiber. Having said that, it is clear that lasers offer a number of exceptional attributes that ensure selective, highly localized, precise, and controlled cleaning with very low environmental impact and simple health precautions, on the condition that we wear the appropriate glasses and we take all the precautions. Lasers are absolutely safely. Laser systems are not as cheap as a scalpel, for example, but in our days, plenty of solutions allow us to consider that cost is not a problem when it comes to choose a laser for our laser cleaning application, for cleaning applications. I have here a couple of, I have a cartoon that was meant to show how the difference between laser cleaning and microabrasive, based mainly on the fact that lasers are absorbed by the material that needs to be removed, and then the whole process stops as soon as this material has been ablated. And here a couple of photos showing cross sections of limestone. This is some photos that I have taken during my PhD studies in Loughborough University in UK many years ago. The middle photo show the result after a microabrasive, while the photo in the right hand side shows the result after laser cleaning. As you can see, the patina is greatly safeguarded when it comes to laser cleaning. Um, Laser cleaning relies on the ablation effect, and this refers to the removal of material as a result of irradiation with an intense, short pulse laser beam at wavelengths that are strongly absorbed by the material. We have here, I don't know if you can see my, let me see, I have a laser pointer. We can have here a material and a laser beam reaches this material. Part of this will be absorbed, part of this will be reflected, and some part of this will be transmitted. And there is an equation saying that the three of them will be equal to the initial energy. So in most of the cases that we have to deal with laser cleaning challenges, reflection is negligible. This mainly refers to metallic surfaces and when they are very polished. Our main attention is to the cases that the laser beam is absorbed by the material. And here we want to have the maximum absorption possible so we can have ablation restricted to a certain area. It is important to combine laser and material parameters for the optimal conditions, because we have to remember always that below the material that we want to remove, there is always a substrate. And this substrate is the one that we want to safeguard because it has all the historical information. So this is something we need always to keep in our minds. Okay. And this is a graph that we all call etching rate. It shows how much material is removed per pulse for different laser fluencies. I'd like to draw your attention in these two values. The blue dot refers to the onset of material removal for the encrustation. So about 1.8 joule per centimeter square are necessary for this case of marble and crust to start removing the encrustation, while the white dot refers to the damaging threshold for the stone. So there is plenty of space between these two thresholds to remove the crust without damaging the substrate. And this is what we call self-limiting character of laser cleaning. Of course, here there is a drawback, and this is quite an important issue in conservation, that in certain cases it has been reported that some surfaces turn into yellow. And this was a problem that has been carefully and systematically investigated in the heritage research, and I will come back to this later. And I have another photo here, which is from a research 25 years ago. And you can see here the similar etching studies for sandstone and a typical encrustation for the infrared and 3 UV beams. And you can see that only in this case, we have this safe distance between the threshold for the removal of the crust and the threshold for the damage of the stone. The rest of the thresholds are very close and does not allow us to be confident that we are in a self-limiting regime. As you can see, plenty of studies for more than 30 years now have thoroughly investigated different materials different ablation regimes and using different and various laser cleaning systems. And I think it's clear by now that for each individual cleaning challenge, an optimum laser cleaning methodology can be defined. I have to say that there are the physical, the chemical properties of the materials, as for example, the absorption coefficient, the thermal conductivity, and so on, that they are decisive for the quality of the cleaning intervention. For materials that absorb highly the laser light, laser ablation is effectively taking place without any undesired side effect. And given that the properties of the material are inherent and cannot be changed, a safe and precise laser cleaning process can be influenced and controlled by the careful selection of the characteristic of laser light. So the wavelength, the intensity, the pulse duration, the repetition rate are among the parameters that can be selected for an optimal laser cleaning treatment. Of course, there are other factors like the environment, whether we are using some water to enhance the cleaning, etc., that can also influence the result. But it's very important to know that a proper optimization between the physical properties of the material we want to remove, the physical and chemical properties of the material we want to safeguard, and the laser parameters is essential. And here I have cartoon aiming to show that when a laser beam is focused on a material, the etching depth, the material to be removed for each laser pulse is closely dependent to the absorbance of the material. This is the optical penetration depth. So the highest is the absorption, the lowest is this depth. And our laser cleaning treatment is very precise and of high resolution. On the other hand, there is also this thermal diffusion length, and this is the area that is affected by thermal effects, and this can be minimized having in our minds the appropriate conditions to minimize, for example, the heat capacity of this combination of materials. Um, for an optimal cleaning methodology, it is essential to approach each laser cleaning challenge cautiously, and therefore we initially employ very simple and simplified models, and these are used to set the laser parameters. Then we test them on technical mockups and coupons, and finally we fine-tune the methodology on objects of lower historical value. And this is how we approach every single cleaning challenge. Okay, in my talk today, I will describe a number of different laser cleaning approaches based on 4 highlights, 4 clinic challenges that we studied in our laboratories. Let's start. First of all, we have Hermes. This is an oversized marble statue that was found in Peloponnese, and this refers to the removal of hard and thick encrustation of aluminosilicate composition or marble. We did some preliminary studies and no gypsum was detected. The crust is rich in alumina and silica, so we have a very specific condition. We have coloration to the oxides from the burial environment, and we have a different adhesion level of the crust to the marble according to the condition of the stone. What we did is to take some samples from the excavation site and perform some microabrasive, ultrasound, and laser cleaning tests. When we compare these tests and studied them thoroughly in the lab, we were able to indicate which is the optimum result and which are the conditions that have to be followed for this cleaning challenge. I have to say that although these seem quite trivial now, if you remember that this study took place back in 2000, 2001, you can understand how important it was at that time to prove that these techniques have certain results and can be comparable. As we said, this is a straightforward laser cleaning case. We have self-limiting conditions, and the marble statue was cleaned using a Q-switch and the E-RIHS system very easily and nicely. I'd like to show you a detail of this cleaning, as this shows very nicely how the encrustation was removed and the marble surface was revealed without affecting the crystals of the marble, which, as you see, they are very visible and very fragile. You can find further information in this publication. A similar approach was followed recently when we had to clean this amphiglyph from the Museum of Ancient Elefthera in Rethymno. This amazing relief came to our laser laboratory, and together with the conservators of the Acropolis Museum, we were able to clean very nicely this marble piece and reveal all this sculpting information before the exhibition of this object to a exhibition that took place in Rethymno last summer and autumn. Okay, let's go to the next case, and this refers to the laser-assisted removal of dark pollution crust from marble. This is a different situation for many different reasons. First of all, because it has a lot of organic compound in the composition of the crust, and also because this is the case where discoloration and yellowing was mainly reported. To deal with this particularly challenging cleaning problem, we developed a methodology that we employ two laser beams, two wavelengths, and we combine them in one beam, and we were cleaning with this one. You can see here a test area using the 1064 nanometer in the infrared of a neodymium E-RIHS system, a UV of the third harmonic at 355, and their combination. I'll give you more information on this. So practically, we use a Q-switch and the E-RIHS laser, and we employ the harmonic at 1064 and the fundamental at 1064 and the third harmonic at 355 nanometer, the two beams together in spatial and temporal overlapping. What we can regulate is the ratio, and this allows us to reach to different cleaning levels. This methodology was developed and applied for the Athens Acropolis sculptures and monuments. In order to do that, we collaborate with the conservators of the Acropolis Restoration Service, and we were given some corner additions. As you can see, these are the pieces that have been used in the monument to ensure stability of the frieze. These are made of different marble of the same corridor, and they have the same encrustation problem like the rest of the sculpture. So we were able to take these marbles, do all our tests, and be able to analyze and evaluate destructively using different methods in order to ensure that we reach to the best cleaning result. The first assemblage from the Acropolis to benefit from this laser cleaning methodology was the Parthenon West Frieze. You can see here an example of one of these blocks, block number 3, and you can see here the area at the back side of the hose that has been laser cleaned. The difference is amazing, as you can imagine. Later, the methodology was applied to clean the coffered ceiling of the Caryatids ports in the erectio prosthesis. Here we have a very challenging site application. We had to move on site with all the tourists visiting the Acropolis hill. We had to restrict the area and to create a nice small laboratory inside this porch. And what's next? Next is the Acropolis Museum and cleaning the real caryatids that they are exhibited at the museum. Uh, Practically what we did was to create open to the public laser laboratory in the museum. We built a platform together with the restoration team of the Acropolis Museum, and our aim was to open all the procedures that were usually hiding inside the laboratory to the public. And for this reason, we had the Keck Award back in 2012. I have a small video that this is, let me see, I have to take the pointer, I think, so I can have this video running. And in the right-hand side, you can see some numbers that the conservators have recorded. We have 4 sculptures, 200 mappings of the work that has been done, 5 conservators, 1 laser technician, 600 working days, etc., etc. You can see the conservator applies a thin layer of water and applies then the laser. There is always some recording of the parameters and so on. You can find this video if you'd like to reach it again in the homepage of the Acropolis Museum under the subject of laser cleaning. This is the YouTube of the Acropolis Museum. So let's go further. Having the experience of this laboratory in the Acropolis, our team, together with the effort of Athens Antiquities and Raymetrics, which is a leading company in LiDAR research, developed and joined forces to create CALOS. CALOS stands for the Conservation of Athens Antiquities with Laser and LiDAR Technologies, open to the science and public. And in the center of Athens, we developed a new laboratory equipped with a number of laser analysis and laser cleaning systems. And I'm very happy to present you here our PALAS system, which is a 3-wavelength, a triple wavelength laser cleaning system. This system was developed on purpose, so to use the 3 beams, the 1064, the 532, and the 355 from a Q switch and the YAG laser in combinations of 2, 1064 and 532 and 1064 and 355 in order to approach the cleaning challenges that the effort faces. And these are mainly pollution deposits, burial crust, and biodeterioration. You can find more information in the homepage of CALOS Open Laboratory. And moving to the next cleaning challenge, we have the removal of tarnishing from gilt silver threads in silk textiles. Okay, this is a very, very challenging situation because we have a combination of materials of fine thickness and with different optical properties: silver, gold, and silk. To approach this goal, a series of tests were performed on, for example, tarnished silver thin plates, and then we had tests on silk threads, and then on their combination, and finally on some threads of of a minor archaeological and historical value. Having done this approach, we were able to define the conditions that for this case were the most appropriate. And this was using the green beam at 532 nanometer of a picosecond laser. I have to say that the key point here is the fact that we have also silk, apart from gold and silver. And silk is a very sensitive material, and the 532 nanometer was the only one that would safeguard its composition. This is not, you can find further information in this publication. On the other hand, another particularly demanding challenge refers to daguerreotypes. This summer, we were very happy to welcome to our lab Diego Quintero, who, representing a multidisciplinary collaborative team, brought a couple of daguerreotypes in our labs. The aim was to research the optimum conditions for the removal of degradation layers and degradation products resulting from previous cleaning attempts. And what we wanted was to recover the image uh, and set the safe limits. You can see here the daguerreotype in the laser cleaning setup, and in, let me do that again. Here you can see the image particle that has to be safeguarded, and here some tests with the most promising conditions which were achieved from a 248 nanometer femtosecond laser system. The research is still ongoing, the data are processed, and I hope that soon we will have a publication presenting all this very nice work for your reference. And last but not least, let's move to discuss the laser-assisted thinning of edge varnishing of paintings. Here I have a cross-section, a cartoon of a cartoon of a cross-section of a painted artwork. We have the canvas, we have the primer, we have the paint layers, and on the top of this we have oxidized and polymerized varnish. What we want is to remove this varnish layer or the outermost of this in order to not affect any of the paint layers. This is not a very easy situation, especially when we consider that the thickness of such layers are indeed very, very small. Most of the polymeric varnish coatings absorb highly in the UV. Therefore, our aim is to use UV lasers for such type of applications. And you can see here a number of varnishes and polymeric coatings, and it's obvious that they absorb below the 250 that starts the UV regime. Actually, I have attempt using a cartoon to show you what happens when we use different regimes to remove such type of cleaning challenges. The UV laser beam removes very thin layers of the edge varnish and progressively goes until the point we stop the cleaning process. On the other hand, if we use an IR laser, this is not absorbed by the varnish, so it penetrates the varnish and reaches the next surface. And there it goes secondary ablation or side ablation, you can say it as you like. We have tried with Hirokogu many years ago to present this situation, and I'd like to show you a couple of images. Here you can see this is an aluminum plate covered with paraloid, irradiated at 355. You can see some result. It's not clear what happens, but if you change the focus of the microscope, you can see that there is a crack and the laser beam has not removed the varnish coating, but it has reached the aluminum plate. So practically, we don't have removal of the coating, the polymeric coating, but we have changed to the underlying substrate. And if we go to higher fluencies, we have essentially removal, but we damage the substrate. And similarly to other similar samples, coupons. We can see that in the 248, we don't have a clean etching. Material is not removed in layers, thin layers, but we have some thermal effects. And this is very reasonable because indeed the paraloid at 248 does not absorb significantly. While on the other hand, at 193 that we have high absorption. As we can see here from the graph, we can see that material is removed layer by layer. So practically, to clean with UV lasers to remove the outer part of the H varnish on paintings is a very, very, very delicate situation, a very delicate procedure. I have here, let me see, a cartoon showing a laser beam removing a part of a varnish from a Byzantine icon. This is H varnish together with soot from Gandel soot. The problem is that here we don't want only to remove the varnish, but we have on the back side the paint layers which have very similar properties with the varnish, and therefore there is no self-limiting process. And this is a very important issue. Therefore, a reliable monitoring is necessary. We must find ways to monitor the process and stop it on time. Several techniques, several tools have been used to follow the process and stop it on time. And this spans from imaging, spectral imaging, acoustic imaging, or spectroscopic analysis that allow us to take information while the laser is ablating. One of the first studies took back 15 years ago and was based on spectral imaging. As you can see here, let me show you again the pointer. In this area, processing the photos taken from the spectral camera, we were able to differentiate to the point that, for example, here after 3 pulses, we have some essential removal of the crust, which can be seen in the spectral images. But you can find further information in this publication. On the other hand, LIBS can give us some information. And this depends on the situation. In this case, we have painting, an oil painting that has been covered by multiple layers of acrylic overpaints. The different layers had different elemental composition, and using LIBS in parallel to cleaning, laser cleaning, where we were able to detect from the elements which layer we have reached. And this allowed the conservators to take some decisions on whether to continue or stop the procedure. Of course, in this case, LIBS was not on real time, following real time the procedure. So we were doing some cleaning, stopping, checking with the LIBS, and again and again and again. And further information can be seen in this publication. Okay. We have been also employed laser-induced fluorescence to follow the cleaning process on the basis that most of the varnish layers fluoresce. And here you can see a collaborative effort with plenty of colleagues in which we use painting of less historical value, artistic value, that has been donated for our tests. And we did some cleaning tests, laser cleaning tests, and compare the results with laser-induced fluorescence, optical coherence tomography, FTIR. And at the same time, we did some basic experiments in the lab, and we were able to find some critical thresholds on when to stop laser cleaning on the basis of laser-induced fluorescence monitoring. Of course, every situation is different. One monitoring tool that allows us to have a lot of flexibility and allow us to follow in real time the cleaning procedure is acoustic monitoring, the sound of ablation. In this case, we use an air couple transducer to follow and record the acoustic signals that they are generated upon laser ablation. In all our studies, we have start from very simplistic samples, as I already mentioned to you. So in this case, we start with a marble plate covered with black graffiti. We did a lot of tests in different fluencies, different number of pulses, and we were able to have, by measuring the normalized photoacoustic signal, to have an idea, an image of when we reach the black crust, when we remove the black crust and we start affecting the underlying marble substrate. Of course, we had to proceed to the next level, so we did some further tests on a simulated gypsum-rich crust on marble, and in this case, we follow again the procedure of irradiating the surface and removing the crust. We recorded the photoacoustic signals, but we were not able, from the amplitude of these signals, to get some reasonable uh, explanation. What we did was to use a correlation, cross-correlation data, and in this case, it was possible to differentiate the pulse that indeed reaches the marble. And I have here, I don't know if, yeah, I have here a cartoon that George Levelakis prepared in order to show how nicely this processing of signal of acoustic data allow us to pinpoint the exact pulse that the marble has been reached. And this is a very important issue. You can see. So now in number 5 pulse, we have reached the marble and the situation is like this. And you can see here for different fluencies, we can have these very important onsets. I'm finishing. I just want to show you a couple of nice examples, just mentioning that we had the chance to study the past 2 or 3 years, being a part of the E-RIHS European Research Infrastructure on Heritage Science community. As you know, FORTH has been a Laser Lab Europe facility for more than 30 years now, and since 2009, as a part of the Charisma, Hyperion-CH and Hyperion-HS, we offer our laboratories for performing experiments to approach challenging cleaning cases. So, as part of the FIX lab that of Hyperion HS, which have finished a couple of months ago, we were able and very happy to have these amazing cases. You can see the projects here. I'm not going to give you further information. I just want to show you the different materials that had reached us in order to give them solutions for cleaning. So from all around Europe and beyond, we had the chance to work with amazing objects and challenging cleaning cases. So I think up to now, I have convinced you how important it is to choose the optimal conditions for each clinic challenge, how it is important to find which is the appropriate laser for each different overlayer that we want to remove, and how it is possible to minimize any thermal effects, any undesirable thermal effects or other damages to the original substrate. But what if we use lasers to cause thermal effects? So allow me to close this presentation with a very nice case that came to our lab. And the question is it possible to mend on site the azulejos tiles? The azulejos, you know of them from the Iberian Peninsula. They are very typical, very characteristic, but they are affected by their environment. So we have some cracks, and in order to restore these cracks, the glazed tiles have to go again to the oven. What if we use a laser to mend them locally? So we did some experiments, and they were indeed very, very successful. And as you see, there is a lot of work on this and some patent. I'll finish. I just wanted to tell you that we have initiated several years ago some training summer courses. We had very nice groups of people visiting Forth. Unfortunately, since COVID, we had to stop for a while, but last year we revealed this summer course chance by organizing laser cleaning workshop in the Palace Museum in the framework of our common joint laboratory of Forth at Palace Museum. We were very excited because this started again a new era of summer courses, and now we are creating some novelties, and soon we will be able to show you some announcements for a new idea of laser cleaning and laser analysis summer courses. You can find further information about us in our homepage, and I'd like to thank you for your attention.
Thank you so much for this very interesting presentation, very clear about the laser cleaning opportunities. Before passing to the question and answer session, the next lecture that will be on optical microscopy by Mark Walton on the 27th of March 2025. All the information will be available in the website of E-RIHS and on the social media channels.